Introduction. Fuel cells are an energy source currently in development which produce extremely clean energy by only creating water and heat as a product, and taking a readily available fuel to actually create the fuel. For most fuel cells, the main fuel is hydrogen, although other alternatives do exist. Fuel cells can power all types of items, no matter the size or power requirement. Fuel cells work through two electrodes with an electrolyte in between. The anode is given the fuel, while the cathode is provided air. Using a catalyst, the fuel is separated into protons and electrons, with the electrons flowing through a circuit and actually providing the electrical power, while the protons go through the electrolyte and reach the cathode, forming water and heat by mixing with the air. Individual fuel cells do not produce much power on their own, usually making less than 1 volt each, and as thus fuel cells are usually bunched together into stacks to increase power production. These stacks can have hundreds or even thousands of fuel cells to increase the power of the fuel cell stack. There are also various external factors that can vary power production between cells, such as type of cell, size of cells, operating temperature, and operating pressures. History. In 1839, Sir William Grove discovered that it may be possible to generate electricity by reversing the electrolysis of water. However, it was not until 1889 when two researchers, Charles Langer and Ludwig Mond, began experimenting with fuel cells using air and coal gas. While there were other attempts in the late 1900s at modifying the fuel cell to convert coal into usable electricity, no further attempts nor research was conducted. Francis Bacon developed the first successful fuel cell device in 1932 with a hydrogen-oxygen cell using alkaline electrolytes and nickel electrodes. Despite being the simplest element, consisting of only one proton and one electron, it is also the most abundant element, but does not occur naturally on Earth. Hydrogen has been used for many energy applications due to its high energy content. In the late 1950s, NASA began to build a compact electricity generator for use on space missions. NASA soon came to fund hundreds of research contracts involving fuel cell technology, and these cells have a proven role in the space program, after supplying electricity to several space missions by using liquid hydrogen and oxygen to propel space shuttles into orbit.
There's several ways of providing power on a spacecraft. One is batteries, but batteries, as you know from your use in a car, are quite heavy, can be quite large. Also, you can use something like solar panels, which some of the unmanned spacecraft use going to the outer planets that have to operate for a long period of time. However, they get quite heavy and take quite a large area, so the solution for the problem was to use fuel cells.
The clever idea behind the fuel cell was to use the same hydrogen and oxygen gases which powered the spacecraft's rocket engine. In the rocket, the gases reacted together, creating heat and pressure to push the spacecraft forward. But in the more controlled environment of the fuel cell, the same reaction could produce electricity.
Fuel cells have a lot of desirable characteristics. You can take the oxygen gas and the hydrogen gas that are stored in tanks, combine those together through the fuel cell, and you get water as a byproduct along with the electricity that you want. The water is desirable. You can use that for drinking. You can use it for cooling through the environmental control system. So it turns out it's a byproduct, but it's a very useful byproduct.
In fact, the water that the fuel cells produce is something like on the order of 50 or 60 gallons during a mission. So they produce a lot of water.
Different types of hydrogen fuel cells. The first type of hydrogen fuel cell is polymer electrolyte membrane fuel cells, also called proton exchange membrane fuel cells, and they deliver high power density and offer the advantages of low weight and volume. PEM fuel cells use a solid polymer as an electrolyte and porous carbon electrodes containing a platinum or platinum alloy catalyst. The benefits of PEM fuel cells is that they operate at relatively low temperatures, around 80 degrees Celsius, providing the consumer with a low startup time and less wear on the system components, indicating a higher durability of the fuel cell. However, the components of the PEM fuel cell are costly. Also, the platinum catalysts are extremely sensitive to carbon monoxide poisoning if hydrogen is derived from hydrocarbon fuel. Due to their favorable power-to-rate ratio, they are an ideal source of power to propel vehicles. Most fuel cells are powered by hydrogen, which Direct methanol fuel cells are fuel cells in which methanol is mixed with water and directly placed into the anode. These fuel cells do not have storage problems like the regular hydrogen fuel cells because methanol is more dense than hydrogen. Also, methanol is easier to transport. These fuel cells can be used to power cell phones or laptop chargers. Molten carbonate fuel cells are being researched to use in military, industrial, and utility applications. These fuel cells are high-temperature fuel cells that use an electrolyte composed of a molten carbonate salt mixture placed in a porous, chemically inert ceramic lithium aluminum oxide matrix. Due to the high temperatures, the catalyst for the cathode and the anode can be an inexpensive metal, unlike phosphoric acid and PEM fuel cells. These fuel cells do not require an external reformer or coal generator to convert fuels such as natural gas and biogas to hydrogen. At the high temperatures at which these fuel cells operate, methane and other lightweight hydrocarbons in these fuels are converted to hydrogen within the fuel cells itself by a process called internal reforming. The disadvantage to using this type of cell is durability due to high temperatures, the corrosive electrolyte used to accelerate component breakdown, and corrosion, decreasing cell life. Phosphoric acid fuel cells use liquid phosphoric acid as an electrolyte and porous carbon electrodes containing a platinum catalyst. These types of cells are first generation and are more tolerant to fossil fuel impurities than PEM fuel cells because they are easily tainted by carbon monoxide, since carbon monoxide binds to the platinum catalyst at the anode, decreasing the cell's efficiency. These cells are usually large and heavy as well as highly expensive due to the high amount of platinum that they need to operate. They are also less efficient at generating electricity alone and when not used as a co-generator. Solid oxide fuel cells use a hard, non-porous ceramic compound as the electrolyte. FSOFCs are around 60% efficient at converting fuel to electricity. Due to the fact that this particular cell operates at a high temperature, the catalyst used can be an inexpensive metal, reducing the cost. This type of cell is not very durable, and scientists are currently working on how to create a more durable cell to function under higher temperatures, even as SOFCs would produce less electricity at lower temperatures. Alkaline fuel cells originally used aqueous potassium hydroxide at high temperatures and anti-catalyst, providing a low-cost mechanism. Potassium hydroxide served as the electrolyte, which allowed the passage of hydroxide ions, which was reduced from oxygen gas. Recent developments have allowed for the electrolyte to be replaced with a solid polymer very similar to the PEM, but it was alkaline instead of acidic. The disadvantages are that this fuel cell is easily poisoned by carbon dioxide. Reversible fuel cells work like a regular hydrogen fuel cell, except that there is an additional energy source that converts the water back into hydrogen and oxygen by using a mechanism called electrolysis. Reversible fuel cells can store the excess energy in the form of hydrogen. This energy storage capability could be a stepping stone for renewable energy technologies. How fuel cells work. Depending on the fuel cell, the input fuel may vary, but most fuel cells take an input of hydrogen or some hydrogen-producing gas, as well as having an input of oxygen gas. Some fuel cells, like the molten carbonate fuel cell, require carbon dioxide as well. The basic idea behind a fuel cell is electrochemistry, where hydrogen gas is oxidized using a catalyst into electrons, which flow up through the anode and go into a circuit to make a current, while the protons pass through an electrolyte to the cathode, react with the oxygen gas, and make water as a result, which then leaves the fuel cell. For the oxidation process, the platinum nanoparticles coated onto the carbon layer pull the electrons off the hydrogen gas molecules, separating these molecules into the hydrogen ion, or proton, and electrons. The electrons pass through the anode into the wire, while the hydrogen ions pass through the electrolyte and go to the cathode, where they react with input oxygen. The electrons needed to balance the charges on either side of the equation come from the anode. To calculate the total electromotive force a cell would undergo with its basic layout, you can subtract the electromotive force of the anode from the electromotive force of the cathode, and you would find that in a basic fuel cell, you would produce about 1.23 volts per mole of hydrogen gas and oxygen gas, as well as producing 2 moles of water in the process. The purpose of the electrolyte in the fuel cell is to prevent electrons from passing over to the cathode and only allowing hydrogen ions to pass through. It does so by acting as a conductor to the positively charged. These cells release heat, and by calculating the enthalpy of formation of water, which can be found in any reference table or book to be 241.8 kilojoules per mole at 25 degrees C, we can see that at typical operating temperatures for a fuel cell, which is anywhere from 80 degrees Celsius for a PEM to 1000 degrees Celsius for a solid oxide fuel cell, the enthalpy can increase drastically, being a few thousand kilojoules of heat being released.
Hydrogen fuel cells have an astounding number of potential energy applications. The wide range of fuel cell sizes allow for use in transportation, personal products, and fixed structures. Fuel cells can be used in transportation to provide propulsive power to a vehicle, either as the primary or secondary source of fuel. Hydrogen fuel cell cars have so far seen limited development. However, this is set to change soon, as most major auto manufacturers, such as Honda and BMW, have begun to design prototypes for their hydrogen fuel cell vehicles. Toyota is currently preparing to sell its hydrogen-powered vehicle, the Mirai, as soon as late 2015, the first car of its kind to be commercially available. The hydrogen fuel cell public transportation sector is growing slightly faster, with accessible deployments of buses in Europe, Japan, Canada, and the United States. Smaller, more portable fuel cells can be used in personal products to replace traditional batteries. Uses of hydrogen fuel cell technology in portable personal products include military applications to power on-field electronics, such as night vision goggles, GPS units, and communication devices, small personal electronics, such as cameras and cell phones, and large personal electronics, such as laptops. The main benefit of using hydrogen fuel cells in personal portable products includes longer operating times compared to traditional portable power sources, faster recharging, and significant weight reduction when compared to batteries. Fuel cells can also be used to power small buildings, such as houses, or even large buildings, such as entire manufacturing facilities. Hydrogen fuel cells can be used as a source of daily heat and power, or as a source of reserve or emergency power. A current example of the use of hydrogen fuel cells in buildings is the Coca-Cola East Hartford bottling plant. It is run partly off of hydrogen fuel cells and is expected to reduce energy consumption by 30%. Hydrogen-fueled combined heat and power units, or CHPs, for residential use have been sold with success in various countries, such as South Korea and Japan, with over 10,000 units sold in 2010 in Japan alone. Hydrogen fuel cell systems can also be used as sources of reserve energy to provide a guaranteed supply of power in the event of an emergency. This can be extremely important at locations such as hospitals and telecommunication and emergency radio communication stations during a natural disaster. Fuel cells have a surprising number of advantages when compared to conventional power sources, such as internal combustion engines or batteries. These benefits include: hydrogen fuel cells have greater efficiency than diesel or gas engines. Sound pollution is minimal compared to traditional combustion engines. Thus, hydrogen fuel cells are ideal for use at locations such as hospitals or military bases. Fuel cells eliminate pollution caused by burning gasoline or diesel, since the only byproduct created by hydrogen fuel cells is water. If the hydrogen used to operate the fuel cells comes from solar-powered electrolysis device, then greenhouse gases are eliminated entirely. Since hydrogen can be produced anywhere where there is water and sunlight using the solar-powered electrolysis method, generation of fuel can be done anywhere. Low-temperature fuel cells are ideal for military applications, as they are not detectable by infrared homing. Hydrogen fuel cells do not have a memory effect, an effect that causes batteries to less effectively hold a charge when they are recharged. Maintaining hydrogen fuel cells is simple compared to complex internal combustion engines, since they contain fewer moving parts. However, there are also disadvantages to using hydrogen fuel cells. Hydrogen gas is difficult to store, distribute, and transport. Hydrogen is also extremely flammable, so a malfunction in a fuel cell can be potentially hazardous. Hydrogen fuel cells are also very expensive to produce. The starting price for the Toyota Mirai is $58,325.
Alternate mechanisms for hydrogen fuel cells. Each fuel cell has its advantages and disadvantages, and as such, removing the disadvantages of any particular model would be improving the mechanism for such fuel cell. For PEM fuel cells, the major drawback to them is the cost of the catalyst, and how easily these catalysts are poisoned by carbon monoxide, requiring additional hardware in the form of a reactor to minimize carbon monoxide. The obvious solution is to find an alternate catalyst that can work with the fuel cell, and active research is being done to find these alternate catalysts. One such research was done by researchers at Max Planck Institute for Solid-State Research in Stuttgart, who are working on an organic catalyst that would operate the same as the platinum catalysts do for the PEM. For hydrocarbon fuel cells, the best way to maximize energy and minimize costs is to avoid using reactors and just going for high temperature fuel cells in order to allow the hydrocarbons to undergo internal reforming, or when the hydrocarbons are separated into hydrogen gas and natural gas products without external input or reacting. For alkaline fuel cells, the main drawback is carbon monoxide poisoning of the cell and the cost of limiting or removing the carbon dioxide to and from the cell, and such development of equipment to filter input gases, or develop technology to purify carbon dioxide from a cell more efficiently are possible solutions to fixing these types of fuel cells. Most other fuel cells use natural gases or fossil fuels to power themselves, which defeats the purpose of the clean hydrogen fuel cell, and is thus the best solution for said fuel cell is to implement the successful methods these fuel cells use into existing hydrogen fuel cells to improve input with only hydrogen. Fuel cells have a long way to come, but improving what we already have is the best step to progress we can take to making this technology extremely practical.